over, so that should be fine. So, this is my good friend Matteo Cremonesi. I've known Matteo for a number of years on the CDF. We've worked together quite extensively. We're now actually co-conveners of the Top and Beyond the Standard Model group at CDF. And I've known Matteo to always do excellent work. So he is here to tell you about the observation of the single-top process in the S channel. So,
thanks,
please go ahead.
Thank you. So, let me start introducing the main player of the discussion, that is the top quark. So the top quark is the heaviest known elementary particle. So I picked up the latest Bohr combination for its mass measurement, and it weighs all by itself around 170 GeV, and this means that it weighs just like gold atom, but of course by itself, and this is quite amazing. But one of the most important features of the top quark is the fact that it has a short lifetime. This means that we have no hadronization, it does not hadronize inside our detector, but it decays nearly 100% of the time in a W boson and a B quark. This allows us to, recollecting these decay products and measuring their properties, to reconstruct its properties, studying what is basically a bare quark. The top quark was first discovered by the CDF and the Zero collaboration in 1995 at Fermilab. The top quark was discovered in, when it produced in association with its anti-particle, an Untitled Quark. So this process is called TT-bar production. If we have a look at the Feynman diagram on the right, we can understand how the CDF and the Zero collaboration were able to discover the top quark, analyzing just a bunch of events. At the time, they isolated something like 20 events with kinematical properties that are considered as the one of the TT-bar events. If we consider and we compare this number to the thousands and thousands of TT-bar events that we have nowadays at the LHC, it's quite amazing. And how was it possible to discover the top quark in a bunch of events? Having a look at the properties predicted for a TT-bar event, we can understand this because both the tops decay, as mentioned before, in a W and a B quark, and the W decays itself in leptons or quark as well. So we have a predicted final state for this process with a bunch of jets, leptons, neutrino. Some of the jets that are produced are originated by big quarks. So we have distinctive kinematic properties that we can use to isolate quite a pure sample where to look for the top and eventually find it. The TT-bar are produced via the strong force, as we can understand here. We have a blue one that mediates the strong interaction. So the strong production is easier to observe, and it's actually easier if compared to the electroweak single-top quark production. So the quark can be produced not only, via strong interaction, but also via electroweak interaction, and in this case is not accompanied by its antiparticle, it's produced by itself. If we compare the predicted cross-section at the Tevatron for the electroweak single-top production, this cross-section is around 3 picobarn, that compared to the TT-bar 1, that is around 7 picobarn, it's just a factor of 2 lower. But if we compare the signal over background ratio, this number is going down by a factor of 10. This is due to the fact that we have a less distinctive signature for the electroweak single-top production, and this means that we expect to have a higher contribution from the background processes, so all those processes that can mimic the final state for the electroweak single-top production. Factor of 10 lower means that we need 14 years, 50 times the data, and the development of very sophisticated analysis techniques in order to isolate and eventually find the electroweak single-top production. On the right, we can see the two processes that contribute most to the cross-section predicted at the Tevatron, that are the T channel and the S channel. There's actually another diagram that you can use and exploit in order to produce a single top quark that is named the WT where the top quark is produced in association with the W boson, but the cross-section is very small and it's basically negligible at the Tevatron. So we consider just these two diagrams as the diagrams that contribute the most to the single-top cross-section. So after discovering it in 2009, the two collaborations and also two experiments at the LHC started looking for each single process. And the first of the two that was observed was the T-channel. The T-channel was first observed by D0 in 2011, so right after the shutdown of the Tevatron, and it was later confirmed by both the LHC experiments. Of course, the cross-section and S over B ratio is smaller if compared to the overall single-top electroweak production, but we still have discriminating features that we can exploit in order to distinguish this process from the background processes. In particular, let's focus on the light flavor quark that appears in the final state for this the T-channel production. Usually the light flavor jet that is originated by the hadronization of this light flavor quark tends to be more forward. As we can understand from this plot, where the pseudo-rapidity times the lepton charge for all the objects in the final state for a T-channel event are compared at generator level. So you picked up Monte Carlo for T-channel production, you plot the distribution of this variable for all the objects in the final state, and you obtain these distributions. The pseudo-rapidity is a good indicator of the direction of the jet, and the fact that it's multiplied by the lepton charge is a tradition in order to have a distribution that is usable in the analysis. So while the B quark that comes from the top decay and the other B quarks are fairly central, the light quark tends to be more forward. This is actually one of the most important kinematic features that you can use, and it was actually the first kinematic variable that was used historically at CDF in order to try to separate the T-channel from the background. But we also have another feature that we can use, B jet that is originated by B quark, that is as well originated by the gluon splitting in the initial state, is usually really soft. We have a plot similar to the previous one, where the transverse momentum for all the objects in the final state are plotted at generator level. So we can compare the predicted distribution for the light quark, the other the lepton, but especially for the other B. With other B, we mean the B quark coming from gluon splitting. Usually threshold for single-top analysis are around 20-25 GeV, so we can understand that the huge number of events where the other B quark is produced with a transverse momentum that is lower compared to the minimum threshold that we apply in our analysis. And especially if we take into account that it is in log scale, a huge number of events have a very soft B quark. Applying our cuts, the cuts that we usually apply in our analysis, we predict to have an enhancement of T-channel events in sample where we require just one bit jet. So the next step after observing and confirming the T-channel production is to look for the S-channel single-top-quark production. Again, the cross-section is lower if compared to the T-channel, the S over V is still lower, so it's very, very difficult, but it's even more difficult than the LHC. At the LHC we predict to have 5 times more signal, but 15 times more background. This is due to the fact that the S-channel is a quark-initiated process, and all the quark-initiated processes have a disadvantage at the LHC compared to the Tevatron. D0 claimed the first evidence in the summer of 2013, but it was not able to claim by itself an observation.
When you say 5 times more signal, you mean 5 times more cross-section?
Yes, of course. The cross-section is 5 times higher, but we have a factor of 3 more for the cross-section of the background processes.
But you also have more integrated data, right?
Yes, yes, of course, but it's not the only. I mean, it's not a statistical problem when you perform analysis like this. It's more on the systematic side. I will show you later why. But one of the most important background processes, that is the production of a W boson in association with incoherent jets, has a higher cross-section if compared to the signal process. You expect to have a factor of 3 higher cross-section as the LHC because it has also a contribution for processes that are going initiated, and it's usually one of the backgrounds that you know the less.
Yeah, all I'm saying is that bullet is not the whole story.
No, of course, but it can give you a sense. I mean, we are just comparing right now, we are keeping things very simple, not just comparing the total signal event that you expect to have with the total background. So it's just a number that can give you a sense of how much difficult it is to extract such a signal in a background. But of course, there are other features that we are going to confront later in this presentation. So why the S channel is interesting? It's not interesting just because it's a missing piece of our knowledge in top quark production, but it's interesting also because it can hide, in principle, new physics. What kind of new physics? A possible deviation from the standard model may indicate the presence of W prime boson, that is a companion of the W boson, but it has a higher mass, possibly, produced in the S channel. So you basically substitute the virtual W boson that you have for the S channel diagram with a real W prime boson, with a mass that can be high enough to produce a top and a bottom quark in a fast state. So Cdf and D0 both looked in the years for the production of heaviest W prime-like bosons in their datasets, and we are still doing that. I picked up a plot from the latest update from CDF of its W prime search, just to see that it still makes sense to look for W prime boson in the Tevatron datasets, since the Tevatron is more sensitive than the LHC for relatively low mass resonances. With relatively, I mean masses that are above the TP threshold, but still below 500, 600 GeV. So here there's the expected and observed limit from the latest CDF update compared to measurement from D0, CMS, and Atlas. And you can see that both the LHC experiments tend to stop their searches at relatively high mass. And while CDF can go down until 300 GeV, setting right now the best limits in this mass range for W prime production decaying in a top and a bottom quark. So what we are going to do right now is we are going to look for the S-channel single-top quark production in the dataset collected by CDF and D0. CDF and D0 were the two experiments on the Tevatron collider. The Tevatron collider was a PP-bar collider during the run 2 that started in 2001 and ended in 2011. It delivered something like 12 inch femtobarn of data, and the two detectors were able to record 10 femtobarn, each experiment 10 femtobarn. So it was the most powerful collider with around 2 TeV in the center of mass energy until the LHC startup. It was a huge achievement if you consider that the results that I'm going to show you today were obtained 2.5 years after the Tevatron shutdown. So we are still trying to squeeze physics out of these interesting datasets. The two experiments, CDF and D0, were two common multipurpose detectors with a tracking system in a magnetic field, electromagnetic and hadronic calorimeters, and muon system as outer layer. So I'm going to give you an overview of the talk. As we could understand from the introduction, the S-channel signal is really hard to be extracted from our datasets. So in principle, we need to exploit data from both the experiments in order to achieve the observation. As mentioned before, this zero was not able by itself to achieve an observation. So in this talk, I'm going to show you relatively new results from CDF on this channel single-top quark production, a reminder of the D0 result that claimed the first evidence of the process, and the final Tevatron combined measurement. Which are the main analysis challenges that we had to face in this pursuit to the observation of this channel? Of course, we are looking for a small signal in large background. This means that we are, on one side, interested in preserving as much signal as possible, applying a loose set of selection cuts, and we are, on the other hand, interested in reducing as much background as possible. And we require to have beta jets, so jets originated by big quark, at least to reduce the contribution from light flavor production. Unfortunately, the main backgrounds are also the ones with the largest uncertainties. So we need to carefully model, of course, our signal, but more importantly, our backgrounds, but this is not going to be enough. So we are forced to perform a shape analysis using the whole distribution, all the kinematic features that can be helpful in distinguishing our signal from our backgrounds. And we have to face poor separation. Compared to the D-channel, this channel search is of course more challenging since we do not have the powerful discriminating features that I mentioned before that were very useful for to distinguish the D-channel and observe the D-channel. But also compared to the X-search, it has a disadvantage because in the X-search we can use the invariant mass of the 2B jets if we are looking for the X decaying in BB bar to have a good separation from the signal compared to the background. In principle, here we have no resonance to exploit, and this makes this search even more challenging. In order to help ourselves in each of these three steps, we make a massive use of multivariate techniques. Let's start from the event selection. In order to look for S-channel events in our datasets, we apply two different event selection. The so-called LNU-BB event selection, when we require to have one high PT lepton that is either an electron or a muon, as we can see on the Feynman diagram on the left. And we require missing transverse energy that, in this case, it's an indicator of the presence of a neutrino. And we require two or more jets, and at least one of them has to be beta. But at CDF, we also added and used another event selection requiring no isolated leptons. So in this case, leptons are explicitly vetoed, and this makes this event selection orthogonal to the previous one. So we are able to, on one side, recollect all the events that miss, all the S-channel events that miss the requirements for the LNU-BB selection. And we are also sensitive to those cases in which the lepton is a tau lepton that hadronizes instead of producing decaying another electron or a muon. So hadronic taus, even if are not explicitly reconstructed in this case, are included in the so-called MED-BB event selection, are accepted by the so-called MED-BB event selection. The addition of this event selection to the previous one allowed us to add 33% of acceptance, of signal acceptances if compared to the LNU-BB one. So we know that we can identify jets that are originated by a big quark, because when a big quark is produced in the interaction, it hadronizes in B hadrons, and B hadrons tends to have a long lifetime. This means that the B hadron travels in the detector something like 4 millimeters before decaying. This distance is very helpful because looking for displaced secondary vertex is a handle to identify B jets. And in the S-channel search, B tagging is crucial since we do not have so much kinematic features to use in order to distinguish it from the background. And the fact that we predict to have two B jets in the final state for the S-channel is one of the most separating features that we can use. So, as mentioned before, we paid a lot of effort in trying to model all the background and signal processes at the best we could. So we modeled electroweak and top production, and with electroweak I mean the boson production, single top and TT bar. We modeled them using Monte Carlo, normalized to the theoretical cross-section. But for the two most important backgrounds, that is the W plus jet production and the QCD multi-jet production, we couldn't rely on the imprecise theoretical predictions. So for the W plus heavy flavor, we used a model that comes from Monte Carlo, but we extract the normalization from Hayward data. And for the mistags we mean falsely tagged light flavor or gluon jets, we extracted a probability parameterization from orthogonal data samples, and we applied this parameterization to reweighten the Monte Carlo for light flavor production into the signal region. So in this way we are able to control more or less the W plus heavy flavor that, as you can see here, this is the Feynman diagram for the W plus heavy flavor production, mimic very well the final state predicted for the S channel, but also mistags are quite a problem because the diagram is basically the same. You have light flavor quarks here, but since you mistag them, it's a huge problem if you cannot control them. And while for the QCD multi-jet production, we apply a totally derived model for both the shape and the rate. And of course, a QCD multi-jet event can be accepted by our event selection in the case in which a jet is misidentified as a lepton for the LNUBB selection, or of course is more a problem in the MEDBB since you do not have the requirements on the lepton to get rid of some QCD multi-jet event. So the modeling of this background is very, very, very important. Get it right, it has a huge effect eventually. So after applying our event selection, after requiring B jets, after modeling our signal and background processes, let's have a look at the predicted yields for background and signal. And I picked up the table from the Cdf and UBB analysis just to make a point. If we concentrate on the double tag, where we expect to have the largest contribution from signal events, and we compare the total predicted signal rate to the uncertainty on the total background, we can see that the signal rate is lower than the uncertainty on the background. This means that we cannot perform directly simple counting experiments subtracting Monte Carlo from data, but we are forced to use to perform a shape analysis in order to try to extract the signal. And as mentioned before, to help ourselves in each step of the analysis, we made a massive use of multivariate techniques. So the idea it's actually fairly simple. You have a bunch of variables of kinematic properties where there's some separation between whatever you can call signal, that in this case is the blue distribution, compared to whatever you can call background. And you want to use all these features at the same time, possibly also exploiting the correlation that you can have between some of them. And you want to do that deriving one single, more powerful discriminant. You can use such a technique for different purposes. You can use it for betagging. In this case, your signal is a betag jet compared to a light flavor jet. You can use it for background rejection. You can also use to reconstruct that resonance that you miss. We have a top quark in the final state. And as I mentioned before, compared to the Higgs that can directly exploit the Higgs mass, where you expect to have a resonance to distinguish from signal, we do not have it in principle. But we can use multivariate techniques trying to obtain the missing resonance. And of course, the most important part of the story is try to derive a final discriminant that you can use to directly measure your cross-section and see if you have an observation of the process. So let's start from betagging. Both CDF and D0 employ multivariate betaggers. And I picked up an example from CDF, because probably it's the newest one. So at CDF, a lot of effort at the time of the Higgs searches, of the Higgs in BB bar searches, was put in order to derive a new multivariate algorithm that can distinguish B jets from light flavor jets, called HOBIT. So the idea of the HOBIT was to try to include all the features from the previous CDF taggers to derive a more powerful tagger. And on the left we have a plot of the B-tag efficiency, so efficiency with which the Hobbit can tag bit jets, compared to the miss-tag efficiency, so all the times the Hobbit fails, and tags wrongly a light flavor jet. So the curve in black is particularly useful to compare with other previously used at CDF multivariate taggers, like it was Roma and the Venus, and compared to the operating point of the SecVDX. The SecVDX was the historical CDF taggers. It was developed at the time of the top discovery, and it, of course it's not a multivariate technique. It's a series of cuts that can be helpful in understanding if a jet is coming from a big quark or not. So in this plot it appears just like two operating points, but by the way we can see that the black curve is far from all the SecVDX operating points and all the other curves, and this means that the guys that developed it made a good job in trying to incorporate all the features, producing something better. And on the right plot we can see the typical output of a multivariate object that is of course continuous, and you should see some separation from your signal, in this case are bit jets, compared to the light flavor jets. So this study was performed at the generator level, so using Monte Carlos that produce with bit jets in the final state compared to Monte Carlos with light flavor jets in the final state. So the black curve means the black curve is the predicted distribution for the Hobbit output for light flavor jets compared to the one predicted for bit jets. At CDF, the Hobbit was used choosing two different cuts, defining tightly tagged Hobbit jets with jets that show an output larger than 0.98, whatever it is, but just to have a tighter constraint on bit jets, and loosely tagged Hobbit jets with as the name says, loose requirement that is around 0.72.
And I have a question.
Yeah.
Maybe by is it kind of jump?
Here, you mean?
Yeah.
Yeah, I mean, unfortunately, things like this can happen when you use multivariate techniques. And I do not have it right now, but you should see the same plot for the Venus. That was one of the previous taggers used at CDF that has a huge spike around 0.05. Usually neural networks are used like black box. So you picked up a bunch of discriminating variables, you put them into this black box and you obtain one variable as an output. And this has pros and cons. It's pretty fast, but you should be able to control things like this. The point is that it does not affect the efficiency of the Hobbit. That is what we are most interested. As soon as you can model the output of the Hobbit, or whatever the variable is, properly, so as soon as the data reproduce this bump here, it's not a problem if it does not affect the efficiency. Of course it can be more efficient, but if it does not introduce a bias in your analysis, I mean, you can always use it. So we use multivariate techniques also to reject some background. As mentioned before, the QCD multi-jet production is particularly appropriate for the CDF MedVP analysis. The fact that we do not require to have a lepton in the final state allows more QCD events to fall into the requirements for the MedVP analysis. And here I picked up a so-called stack plot where we have the data distribution predicted for this variable that is NMQCD. I'm going to show you, I'm going to tell you what it is, but for the moment we have a data distribution with all the Monte Carlo predictions superimposed. So as we can see here, and here we are in the two-jet double tag subsample that should be the most sensitive for our signal production. Basically the plot is blue, and blue means QCD multi-jet. So we cannot see anything if we are not able at least to reject a large part of QCD events. So this variable here is actually a neural network. So it's a multivariate object that we derived using a bunch of discriminating variables to distinguish the QCD multi-jet production from all the other top and electroweak processes. It works fairly well if you consider the separation is pretty clear, and we can use this variable to, of course, set a cut in order to define the signal region, and so reject QCD events. But it's also useful to extract a QCD normalization in a high statistics region and extrapolate it into the signal region. Here we are. So this process is pretty interesting because we were able to use one of the most important features of QCD multi-jet production, especially if you require high missing ET. And in the case of a QCD multi-jet event, the missing ET arises basically from jet energy mismeasurement. This means that the missing ET tends to be aligned to the direction of the jet that is mismeasured. While in case you have real missing ET, and real means produced by the presence of neutrino, this is not true. It can be whatever. So using all the kinematical variables and angular variables that are connected to these features, we were able to have a good separation between the signal and the QCD multi-jet event. We were able to reject more than 90% of QCD multi-jet events, keeping more than 90% of signal events. And we were able also to constrain the normalization that we extracted in this region to a very high precision, since the fact that this region has a high statistics. And of course, since one of the key in order to extract a small signal in a large background, but especially when the background is uncertain, as I showed before, is to constrain the uncertainty. This is going to be fairly important when we are going to try to extract the signal cross-section. And here we are in our attempt to reconstruct the missing resonance.
How did you pick that 0.7 or something?
Back here, and
55 or something.
What you would like to maximize is the significance of the sensitivity of your analysis to your signal. And of course, this cut.
You will be looking at other distributions for these events in that signal region, right?
Yeah.
And you will do a fit later, or you do a fit here?
No, this variable is just used to reject background. So we are going to have other variables.
So now you would cut at 0.7
Mm-hmm.
or something.
Yeah. So if you're asking me how this cut was chosen, again, you are interested in maximizing the sensitivity to the signal, and you can use a figure of merit in order to do that. Usually you use the signal over the square root of the background, and so you try several different cuts, and you try to maximize whatever the figure of merit you use. If you use the signal over square root of background, you want to maximize that figure of merit. You can compute
So
that.
you actually pick in different values and propagate it.
Exactly, and actually what we did here is also even more complicated, because the signal over square root of background is just one figure of merit. But for example, you can compute that figure of merit for each bin of the variable that you pick as your final discriminant, and then sum them in quadrature to have a better estimate, bin by bin, of your significance. And in order to do that, you have to possibly have different significance for different discriminants for different cuts. Yes, of course. So if you would like to do the things properly, you derive a bunch of different discriminants for each cut on this variable, and you pick up the combination of cut plus discriminant that maximize your figure of merit.
I think the point is that ultimately you're going to do a fit with this.
Yes, of course.
And so the point is that this is not a cut-based analysis. So
Of
the
course.
idea is you're trying to keep a fair amount and you don't optimize on this. You can't look here to see whether
This
it's
is the reason
optimal.
why. This is the reason why.
In some sense, there's not enough here to tell you whether you're optimal or not.
This is the reason why I introduced
So
the
the way it was optimized, you picked various values, you did the full-blown analysis in the beginning where
No,
track signal to
no,
background.
because okay, what you want to maximize, of course, the better is the animal good, no? So if you have to perform the analysis until the fit for each different kind of different cut that you can pick on this variable, it's computationally very expensive. If you do the S over square root of B, as I mentioned before, it's something that is too rough because it makes your analysis closer to a cut
If
base.
you only look at this distribution and you're planning to do much more after that, then signal over square root of background or signal over
It's what we
square
did.
root of background edited course is still not the right
Yeah,
variable, right?
yeah, of course. But if you, but as I mentioned before, if you pick your final discriminant variable, the one that you are going to use in the fit, and you perform you compute the S over square root of B, beam by beam, and you sum in quadrature, you have a good estimate of what is going to be the sensitivity of your analysis once you perform the fit. And this is what we did. Yeah, on the other distribution, not on this. Of course, these bins are always the same. Whatever you cut, the bins are not going to change. You are interested in the bins that are in the variable that you are going to actually use for your final fit. What would you call your final discriminant? This is not our final discriminant. It's just a discriminant that we used in order to reject some background and eventually have an advantage when we are going to use the other discriminant for the final fit. So, okay, and yeah, and okay. Here is our attempt to reconstruct the missing resonance. So both the Cdf analysis, the NUPP and the MetPP analysis, employ a multivariate algorithm to try to understand which is the bit jet that is originated in the decay of the top quark. This is fairly important because summing it together with the other objects, so the lepton and the missing T, you can in principle reconstruct a lot of kinematical variables. Among them, of course, the most important one is the reconstructed top quark mass. And here is the plot that I picked up from the SCMS and NUPP analysis, where where I have the data distribution and superimposed to the prediction for background and signal in the reconstructed top quark mass. So you can see that the distribution peaks at the right point. Of course, you pay the price to sculpt a little bit the background processes. But in any case, this turned out to be the most separating variable for the Cdf and NUPP analysis, making the effort in trying to reconstruct this variable.
But it has not been used in neural net, right?
What?
It has not been used in neural net, this variable.
This is not a neural net, but it was reconstructed using a neural net. So in this case, the output of the neural network is connected to the probability for a bit jet to coming from for a top quark. So event by event, you picked up the most probable jet coming from top quark decay, and you sum it together with the lepton and the neutrino, and you reconstruct this variable.
So just in the selections before it was not used.
Yeah. And the final step is to derive a final discriminant, that is the real variable that we use in the final fit. So I picked up an example from D0 because it's fairly complicated and convoluted. D0 performed 3 different analyses using 3 different multivariate techniques that were eventually combined in a unique Bayesian neural network used as final discriminant. So here we have the output of the Bayesian neural network with the distribution of data superimposed to the backgrounds. And so let's focus on the most significant bins that are the one around 1, where we can see that the predicted distribution for signal events, so in light blue, for TB here we mean S channel, and let's compare this distribution to the uncertainty on the total background, that is the shaded area here. So the discriminant is working because finally, beam by beam, we have an uncertainty that is smaller than the predicted signal, and this is what we wanted. Here, in order to match data, we really need to have the signal to fill the gap between the background prediction and the data distribution, because the background by itself cannot do that, since it's forced to flow. It allowed to move in the shaded area.
It's just systematic answer.
This is post-fit, is statistical and systematic. is the sum of the two.
Yeah, but not the variance, so just if I would compare it to data, I would still take a square root of, I don't know, call it something in the first plane, right? Yes.
This is the uncertainty in the prediction, not the uncertainty, not, yeah, on the year.
Yeah,
That's why. it's
Beam by
small,
beam.
Right.
so is the 1 sigma shift. Okay, and this uncertainty obtain an extra constraint also from the less significant bin, because this region here that is background populated and since it has a high statistics is get an extra constraint from the data distribution by itself. So this means that of course in these bins the background is in principle free to flow between the +1 sigma and -1 sigma shift, but you have also to consider the less significant bins that are gonna constrain those backgrounds more than just the uncertainty, the shaded area that is shown here.
Can I have a question?
Yeah.
So if you have a different kinematic variable, that's good, so say different technique, two-step distribute, same one to the neural net, then each provide one output to combine the neural net.
No, they're not using, whatever they're showing at the end is not been used in pre-selection neural net, otherwise it will be biased.
Right,
Yeah.
okay, so,
Yeah. So from here we can see that the data distribution clearly prefers signal path background hypothesis, but we would like to use, we do not want to do things by eye, but we would like to use this distribution in order to measure area cross-section. And in order to do that, we use the Bayesian approach. So we perform the likelihood fit to the bin final discriminant distribution using, since it's Bayesian, a uniform non-negative prior for the signal cross-section. Non-negative just not to access to non-physical regions, of course. All the uncertainties on signal and background normalization and shapes are included in the final fit. So which are the systematic uncertainties that we included? The most important one, of course, is the one on top of the normalization of W plus jets, because W plus jet background is the dominating one and one of the most uncertain. And we took care of correcting our jet energies at our best, and in order to do that, we correct separately port jets from ground jets, and we have two different uncertainties on top of two different corrections. We also included shape uncertainties, especially when we have a data-derived model for the shape of our kinematical distribution. We are forced to use and to propagate shape uncertainties. And in the plot on the right, I'm going to show the shape uncertainty on top of the QCD multi-jet data-derived model in the Cdf MatPB analysis, where you can see in light blue the -1 sigma shift, and in purple the +1 sigma shift that are properly smoothed and symmetrized compared to the nominal that should be a straight line at 1. So after including all the uncertainties and performing our cross-section measurement, we also would like to understand how much significant is our measurement. In order to do that, we calculated the p-value. The p-value is the probability of observing a signal that is as large as or larger than the observed one just from fluctuation of the background. And usually an ensemble-based calculation is used. This means that we simulated a lot of times our experiment, and in signal plus background and background only hypothesis, and we compare these two hypotheses to understand which one is the most suitable. I'll start showing you some of the results, and I'll start from the results from the Cdf analysis. So the strategy at Cdf was to take advantage of all the improvements introduced in the X-search, since comparing the predicted final state for a single top event to the predicted final state for the most sensitive channel at the Tevatron, that is the associated production of a W boson with a Higgs boson and the X decaying in PB bar, basically the final state is the same. So the idea was to import most of the improvements that were developed at the time of the X search in this S-channel search. Specifically, we inherited the event selection, since the NUBB event selection I showed in detail before is basically the selection for the WH analysis, with the W decaying in lepton neutrino and the H decaying in BB bar. But also the MedBB event selection comes from the ZH with the Z going into neutrino analysis. And as mentioned before, the OBIT tagger is employed, and the OBIT was derived at the time of the X search. But also the fitting strategy is pretty close to the one applied in the X search, since we included the rechanneled single-top-quark production as a background constraint to the theoretical prediction. And so let's start with the result. This plot shows the posterior probability density distribution for the single-top S-channel cross-section extraction in the MedBB analysis. So in the MedBB analysis, we were able to measure a cross-section of 1.12 in agreement with the standard model prediction of 1.05, with an expected uncertainty of 57% and observed uncertainty of 53%. The fact that we have a smaller observed uncertainty compared to the expected uncertainty is due to the fact that in the final fit we are going to gain that extra constraint I was mentioning before from the less significant bits of our final discriminants. When we computed a p-value that returns significance of 1.9 sigma observed compared to 1.8 expected. And we did the same for the LNUBB analysis. Here we have a cross-section that is slightly higher than the predicted one, 1.4, but is still in agreement considering the uncertainties. And the uncertainty is 38% expected and 30% observed. Again, the less significant bits are constraining our backgrounds better than the predicted uncertainty. So here we were able to claim an evidence, a 3.8 significance evidence compared to a 2.9 sigma expected. But right now we have two different analyses that analyze two orthogonal data sample at CDF. So it was worth it to combine the two in order to try to have the best possible answer out of CDF on the S-channel single-top-quark production. So you can find more details on the two analyses and on the combination in the paper that are mentioned in this slide, but we did not perform a simple combination starting from the result. We reperformed from the beginning our statistical analysis, collecting all the bins coming from all the subsamples of the two CDF analyses. So, and then we reapplied our machinery, our statistical machinery, in the attempt to extract the single-top S-channel cross-section. And the combined measurement turned out to be 1.36, still in agreement with the standard model prediction, considering the uncertainty. We had an expected uncertainty of 33% compared to an observed uncertainty of 25%, so the measurement was fairly precise. But most importantly, we we calculated the p-value and we extracted the significance that turned out to be 3.4 expected compared to 4.2 sigma observed. So 4.2 means strong evidence of S-channel production from CDF, but it was not enough, again, to claim an observation by itself. I picked up this plot for the CDF combined significance to make a point on how much difficult it is using an ensemble-based calculation to derive the p-value when you have basically a high significance for your signal. So in this plot is shown the cross-section over the standard model prediction measured in each single pseudo-experiments generated at CDF in order to make this calculation. So the red curve is formed by measured cross-section for all the pseudo-experiments generated in background-only hypothesis. The blue curve is the same curve, but with the pseudo-experiments generated in single-pass background hypothesis. So after generating something like 600,000 pseudo-experiments in both the hypotheses, you feed them, and you obtain this distribution in the two different hypotheses. In order to calculate the expected p-value, you pick up the median of the blue curve and you compute the integral of the red curve starting from the median. That basically means counting how much points you have on the right of the median. In order to obtain the observed p-value, you do the same calculation starting from the observed value. So it took some time, computationally speaking, in order to generate 600,000 pseudo experiments in both hypotheses. It basically took 10 days for me running with 4 different accounts, and I don't know if it's properly legal, but by the way, this means that doing this calculation implies several different kind of difficulties, also the legal ones. And so I'll give you now a reminder of the D0 result. D0 applied a slightly different strategy compared to the Cdf one. So they used a two-dimensional multivariate discriminant that is sensitive simultaneously to both the S-channel and T-channel production. And here on the left you have the two-dimensional posterior probability density distribution, when on the x-axis you have the S-channel cross-section and on the y-axis you have the T-channel cross-section. So in order to measure the S-channel cross-section, what they did was integrating over the y-axis. And this allowed them to obtain an S-channel cross-section without assuming the standard model S over B ratio. This makes the measurement less model dependent than the Cdf one. And applying this strategy, they were able to measure a cross-section of 1.10 observed, that is in agreement again with the theoretical prediction, with an expected uncertainty of 29% and an observed uncertainty of 29% again. And one can ask why in the D0 case we do not have the usual trend of having an observed uncertainty that is smaller than the expected uncertainty. This is due to the fact that they apply a more aggressive prefix systematic uncertainty on top of the W plus Z background, so they use a more updated calculation for that specific background, so that their uncertainty is not data derived, and use a smaller prefix uncertainty. So in the D0 case, one of the most important background is constrained from the beginning with a smaller uncertainty. So they were able to claim the first evidence with 3-point sigma significance observed. So again, neither of the two experiments was able to claim observation by itself. So the idea was to try to apply the same strategy we applied at CDF and perform a final Tevatron combination to see if merging and using at the same time the two data sets, we are able to claim observation. So a slide that is pretty close to the previous one. So these two plots were already shown in the previous slide, but now we add another plot that is coming from this view. Again, the combination is not performed starting from the results. We performed our statistical analysis from the beginning, collecting, in this case, all the bins coming from all the samples of all the analysis coming from the two experiments. These, of course, you have to face a lot of difficulties in order to do that, a lot of codes that crash, and a lot of problems to solve, but it's a price that it's worth it to pay, because you not only double the statistics, but you can have an extra constraint on your systematic uncertainties, considering two different data sets. Of course, on the systematics that can be correlated among the two experiments, for example, the uncertainty on the luminosity due to machine effects. We adopt for this strategy, for this combination, the CDF strategy. So we are using just the S-channel optimized monodimensional discriminant from D0. We collected just that input. And we constrain the T-channel to the standard model prediction also in the D0 case. So in this combination, we assume the S over T ratio from the standard model. And so again, we are collecting a lot of pins, and the best way probably to show them...
You're constraining the ratio or the total cross-section?
No, the sigma s over sigma t ratio.
So you're correct.
Once you assume the t-channel, of course you're assuming the standard model ratio.
No, well,
Yeah.
if CDF is observing a higher than standard model prediction for S.
Yes.
And T and.
Assuming the t-channel. So, yeah, of course, the post-fit ratio, it depends on the measurement, but it's the pre-fit ratio, the one that you assume. The zero does not.
I just wanted to make sure.
No, I mean, the fact is that the zero for their measure for its measurement does not assume the pre-fit S over T ratio, because the two cross-sections are measured simultaneously. So, by the way, all the bits that we collect, it's the best way to show them is trying to put all together in one plot, no? Using a figure of merit that can be interesting. So we collect bins with a similar S over B ratio, and we sorted them using this figure of merit. So you expect to have the most significant bins, the one with a highest S over B ratio, around 0, considering that this is the log of this figure of merit. And in fact, we zoom these bins just to make a comparison of the delta distribution compared to the background distribution. And we play the same game again. In white, you have your background prediction. In the shaded area is the total uncertainty on the total background. The delta distribution does not match the background distribution. And so you really need the blue signal in order to fill the gap. And here the blue signal, of course, is larger than the expected, than the total uncertainty on the background. So, but if we subtract the background from this plot, we see that we are actually sensitive. We have another region where we are sensitive to the S-channel production. And this is due to the fact that the less significant bins, as mentioned before, are constraining background uncertainty at the level that around -1 the signal appears above the shaded area. Using these bins, we performed again, we applied our statistical package, and we extract our measure cross-section.
That actually suggests that your background is overestimated.
Where?
The uncertainty in the background is overestimated.
Yeah, of course, as it is. At least at CDF. When the uncertainty that at CDF we have on top of the W plus Z background is overestimated to consider several different effects that are not considered a priori. So in order to fix those effects a posteriori, you apply a larger systematic uncertainty than the one that you are supposed to apply. But you rely on the fact that you have background populated bins to constrain that background. You can see these as you are simultaneously measuring the rate of your most important background and your signal rate.
So this is your sort of a priori background uncertainty as opposed to your post-fit uncertainty. Something. Yeah, all right.
The a priori uncertainty is very conservative.
Right, is the
but,
point.
but that's what you're showing here is the a priori, even though the constraint significantly reduces that.
Yeah, I mean, it's a strategy that you can apply. You can say, okay, I do not want to rely on the precise knowledge that I have of this background,
Yeah.
and I want to measure it.
But
And you know-
it's just an ambiguity that it says background uncertainty. It's not whether it's the posterior uncertainty, it's the prior uncertainty.
I mean, this is posterior because everything is observed in this plot. So what I'm showing is that the data is able to constrain our background at the level of making the signal appear around -1, where -1 means less significant bins, so with a larger background contribution. But actually, you can have a large background. It's not the problem. It's the uncertainty on top of the background that is the problem. As soon as you are able to constrain the uncertainty, you can have whatever number of background events you want, and you are still able to see signal. It depends on the knowledge of the background. That can be a priori, as the zero does, that use a most updated calculation for W plus Z. So it can be a posteriori as we did, fitting it directly in the final fit. So the measured Tevatron combined cross-section is 1.29 with an expected uncertainty of 20% and an observed uncertainty of 19%. This measurement is fairly precise, and it's going to be probably the most precise channel cross-section measurement for some time. And it's still in agreement with the standard model prediction, even if it's slightly higher compared just the central value, if we compare just the central values. And in this summary plot, you can see all the measured cross-sections from all the experiments compared together, just to have a cross-check to see if all the measurements are consistent with the others and consistent with the standard model prediction, that is this line here. So we can see that all the measurements, considering the uncertainties, are compatible with the standard model prediction.
But all four on the right.
Hmm?
All four on the right from this area.
Yeah, I mean, but you have an uncertainty. And
That
it's...
will add another, you know.
Yeah, but the CDF combined is not independent, right? This is a little unfair.
Three.
Yeah, I
There are
mean,
only 3 independent measurements, even though there are 5 things shown.
okay, you can look at this plot.
Right, so you have,
Yes, either you
it's 3 out of 3.
either you not consider this line or you do not consider
Oh, I
the
excluded
previous.
the last one, but I missed the third one is a CDF combined.
Yes.
Okay.
So CDF has quite, I don't want to say an excess. I mean, we measure a cross section that is slightly higher than the predicted one, but it's still in agreement with the standard model considering the uncertainty. D0 does not see this effect. The combined measurement is pretty close to the standard model prediction. I mean, there's no room to suspect that there's new physics in this 1 sigma deviation. But by the way, it's of course interesting doing this cross-check before saying anything. And once you are pretty confident that all the measurements, considering the uncertainty, are consistent with the others, I mean, you can go ahead and try to see how much significant you are to the S channel. That is what we did. First of all, okay, we have an equal contribution from CDF and D0. This means that the weights of the two measurements, of the combined CDF measurement compared to the D0 one, are almost the same. And we have a negligible top mass dependence, so if you are gonna, the point is that all these measurements are performed assuming a top mass of 172.5 GeV. That is slightly different from the measurement that we have right now, that is 173.3. But we checked the dependence on the top mass, and it's basically negligible, considering the 19% uncertainty of over the combined Tevatron measurement.
Why is the combined result closer to CDF than to D0, even though they have a small uncertainty?
How can you say this closer?
Well, you know, like 110. and
Because 36 minus 29 is 6, while it's...
right in between would be 124, right? 23.
I mean, if you perform a simple calculation, summing and quadrature the two cross sections, subdividing by 2, of course, you do not get this number. But if you do this calculation on the expected values, you get exactly the Tevatron combined expected number. The point is that this is not expected, this is observed. Once you go on data, you never know. And this is what it happened. So, okay, we are more or less confident that we are doing right because of the measurements are consistent with each other. So why not? Why not?
Some beans lit up even more.
Yeah, exactly. This is the point. This is the point. And you don't know. Probably are the CDF beans or probably are the D0 beans. But since you correlate some uncertainties with CDF data, you don't know. So by the way, it's worth it try to understand how much significant we are on the S-channel Single-Top-Quark production, and in order to do that, we didn't perform the previous ensemble-based calculation for the reasons I mentioned before. So we used an LHC-style asymptotic approximation. First of all, we are using a different figure of merit as test statistics. We were using the normalized cross-section before, and now we are using the log-likelihood ratio, but this is just a choice. Historically, you compute p-values using the log-likelihood ratio. What you do here, you actually generate some pseudo-experiments, but of one order of magnitude less, and assuming Gaussianity for those distributions, you fit the distribution of pseudo-experiments with a Gaussian. And we first checked that we were able, using this approximation, to reproduce the CDF results that were performed, that were calculated using the ensemble-based calculation. We did this, the check was successful, so we applied this asymptotic approximation in order to get the Tevatron combined significance. So here we have the expected, we have the background-only hypothesis in green, and the signal plus background hypothesis in blue. The observed, in this case, is indicated with an arrow. So in order to get the 5.1 significant expected, you, again, integrate, in this case you reintegrate the green curve from the median of the blue curve, and then in order to get the observed, you perform the same integration starting from the observed value. So we have 5.1 sigma expected compared to 6.3 sigma observed. So finally, combining the inputs from the two experiments, we were able to claim the first observation of the channel Single-Top-Quark production. And this leads also to my conclusion. So
your reported p-value depends on standard model prediction for the cross-section?
I mean, when you generate pseudo experiments,
You said you include the integral in the blue curve?
I mean, the calculation is performed integrating the green curve starting from the median of the blue curve. Of course, the blue curve is
That's the expected, but what about the observed?
the observed again is on data.
It's just the probability of that.
Yes, you compute the log likelihood ratio considering the value that you obtain on data. So again, it's easier to see what observed means if you use the normalized cross-section, because when you use S over S standard model, the S is the cross-section that you measure. But you, of course, can compute the log likelihood ratio considering the data, the result that you obtain on data. And you have a value in this plot here. And then you integrated the green curve. So this tiny integral here is exactly the 6.3 sigma deviation that we see on data for single-top channel production. So again, we are not assuming the you are assuming the standard model when you do the expected.
No, fine. I just like when you were explaining, I misunderstood what you said.
Okay. So conclusions. I showed the zero first evidence for a channel Single-Top-Quark production with 3.7 sigma observed, and CDF evidence in the combined NUBB and MEBB measurement with a significance of 4.2 sigma. But more importantly, I showed the first observation coming from the combination of the measurements from CDF and D0 of a channel Single-Top-Quark production with a cross-section of 1.29 and a significance of 6.3. These results are published in PRL, and the PRL was selected to be a PRL editor suggestion. And it's particularly interesting because it's the first observation that requires a CDF plus D0 combination. Previously, in the case of the top quark observation, in the case of the Single-Top-Quark observation, the two experiments were able to claim separately observation by themselves. In this case, we need a combination in order to do that.
Everybody says that if D0 didn't know where the top mass is,
It didn't do that.
they wouldn't be able to do it.
By the way, and okay, this is the missing piece of the Tevatron single-top program that was fairly successful. First single-top observation in 2009, first T-channel observation in 2011, and first S-channel observation in 2014. We are planning to have a final Tevatron combination out soon, where we perform the last measurement that we can perform in single-top events, measuring the VTB, extracting the overall S+T cross-section, and performing a two-dimensional extraction of S-channel and T-channel. Thank you very much.
So questions?
So which part of the result is statistical and so on, and which is systematic?
I mean, this result is systematic dominated. So the statistical uncertainty is around 14%, if I can remember correctly the number from the paper.
So 50-50?
It's, I mean, in quadrature, if you want me to do the calculation, I can do that, but it's slightly dominated by the statistical uncertainty. It's close to 50-50, but...
It's more like 1 to 1.
Yeah.
Any other questions?
You asked our questions, you already talked.
So LNUPB D0 has expected, what was it, 3.7, and CDF was what?
3.4.
Oh, okay, yeah.
No, I mean, let's go ahead and ask the question.
No, is it the, because I thought I remembered, was it 2.8 or something?
It was, I mean, the observed is 3.4, it's 2.9.
I don't
So
care
that-
about observed.
The expected is 2.9, it was my bad, I mentioned the 3.4 while the 3.4 is observed.
So
Yes.
why is 0?
The D0 detector has a better lepton coverage, so they are able to have more lepton events with leptons. This is the reason why at CDF we decided to add the MLBB, just to recover all the events that where a lepton and CDF cannot be reconstructed.
So it's purely the acceptance, it's not so much the...
Yes, it's a detector effect. And I mean, that's also another reason. Okay, now you can compare the expected sensitivity of the overall CDF combination to the D0 analysis, and the overall CDF combination has an expected significance of 3.4 compared to the D0 3.7. So there's still a discrepancy. The D0 analysis, it's a little bit more complicated than the CDF1. And it has, in the selection cuts, a larger acceptance also for jets. And jets are important as well in this analysis. So they are applying a more complicated multivariate techniques to derive their final discriminant, but we checked that this has an effect that is less than 10%, so it was not the key of the reason why they have a better significance. But they are applying different set of cuts that allows them to have a little bit more signal than
So
CDF.
if the coverage is better, then it didn't make sense for them to do that, right?
No, in fact they didn't.
You never know. It's 2 years after the data. So
Now again, you have to find a good balance between the optimal and what you can really do, considering also the manpower that you have. And you can imagine that right now the manpower that you have at the Tevatron, it's all in this room, and so
Close.
so you know, yes, in principle at CDF we could play a little bit with the event selection, but we decided to inherit the event selection from the X because it was the fastest things to do and the more reasonable. So we did the reasonable things, and we got a nice result, considering the fact that the Tevatron was shut down 2 years ago.
Okay, if there are no more questions, let's thank the speaker again.
Thank you.